Okay, so let's proceed with linear regression. This is our fifth session, and we are continuing after a long duration of around 1 month. So it was a gap of 1 month, and chalo, let's start with today. So mainly I've planned with as I was expecting it to be a bit more longer duration today's session, and after also day after tomorrow or tomorrow's session, which will be only 11. So these two sessions I was expecting to be quite long because I have included some more case studies. So let's see how much it takes. So let us start with linear regression. So regarding linear regression, it is one of the most widely techniques and most simple to understand. So all you have to do is just create a fitting line and to know your response variable. So suppose I have a variable which needs to be understood or which needs to be predicted. So that will be my response dependent or a target variable. And on the variable on basis of which I will be making this prediction, those will be my independent variable or my predictor variable. So this is just a basic concept of linear regression, and one most I would say easy to understand and easy to grasp of all the techniques that we have. So these are the few terminologies like if I have only one x variable or my predictor variable, it will be a simple linear regression. Otherwise, if I have more than one predictor variable or independent, or my x variables are more than one, then it will be my multiple regression. So just easy to understand. And there is something called correlation. So I need to understand that if my y variable and my x variable, my dependent and independent variable has some relation in between. So linear regression mainly works with a continuous variable, and when it comes to continuous variable, we need to understand the correlation. In case if it was not a continuous variable and we were working with some categorical variable, then some other test would have been done. But in this case, correlation is becomes quite handy to to understand that how much impact a variable is making on the other. So here are a few examples of correlation, and that if the number of hours that I study and is it proportionate to my grades that I receive towards the end of the year? Is it somehow related? Another could be number of churches building in a city and the number of murders. So is there any association in between? So logically it shouldn't be, but there are some cases where it could have been. Also, like for example, uh, so we are going through winter season, and in this season you're expected to have people wearing more warmer clothes than in other season. So comparatively, the sales of warmer clothes will go up compared to any other uh, season. So temperature here is my determining factor. On basis of temperature, the sales goes up and down. So these are the few, mm, I would say, examples through which you can understand. And only condition for correlation is both the variables should be continuous and numeric. So here you can see there is a scatter plot, which says that if I have a certain amount of correlation between two variables, how my scatter plot should look like. And in case if I don't have any association between the two variables, then how it should look like. So yeah, if you see uh, number of responses by budget online campaign. So as my budget goes up, the number of responses goes high. So suppose if I were to collect a survey and my I have a sub-budget constraint and I cannot accommodate all the responses. But as my budget goes up, the number of responses that I can accommodate also goes high. So there is a linear relation between the two, and it seems to be that both of these have a very high correlation in between. So this is a good example of having a good correlation. On the other hand, let's say uh, It could also be possible that I don't have any relation between the two. So in that case, when I am having a zero correlation, there won't be any pattern. All the number of points will be randomly distributed. You cannot find any pattern. And in that case, your correlation will be near to zero. So scatter plot is a good way to understand that if you're having any trend in between the two variables. Otherwise, correlation number itself can give you the exact figure or an estimate that how much association is there in between two variables. So main definition is this Pearson correlation coefficient. And as most of you must be knowing, that correlation value varies from +1 to -1. So +1 when I have a equation like y equal to x, so it will be directly so same values for both y and x. So in that case, my correlation value will be 1, and in case if my y is equal to minus of x, then it will be negative. So -1 will be my correlation. And in case, as I said earlier, if there is no association between the two variables and both of them are completely independent of each other, there isn't any pattern that you can see in the scatter plot. In that case, my correlation value will be near to zero. So, simple terms, nothing complicated and nothing uh, difficult to understand. So, here is one thing that you need to know, that is the correlation. So, the equation for correlation. So, first is variance. So, variance is for all the values of x, I will subtract it by my mean of x and take a summation of all the square numbers. So, all the square variance that is happening and divided by n. So all of you must be aware of this formula, and this is variance and the square root will be standard deviation. And now there is covariance, that when there is an association between the two variables. So when two variables come into picture, I have something called covariance, and here I have the formula for covariance. And now comes the correlation. So correlation is mainly a proportion, or I can say a ratio between the two. So it is covariance between the two variables, as you can see. This is the covariance between the two and product of variance of two. So this is, so that is, and for that reason correlation value or correlation always is a ratio, and there is no unit associated to correlation. Max +1, minimum -1. So these are all about the ranges of correlation values and what all inference that I can make out through it. So from 0 to 0.25, there will be a negligible positive association. After that, a weak positive association, then a moderate, and then goes on to a strong positive association. So these are the level that you have, and it also depends upon the data set that you have, how good your data set has been tracked, and how good you have been able to, trace all the values of all your variables. So also depends upon the quality of data you have. And there is something that you need to be cautious about. So correlation value could be good, but at times it could be misleading. So here I have listed out few of the examples that shows there are high correlation, but that was quite misleading. So let us understand what was that and how that has you know misleaded the entire process or entire findings. For example, let me take an example. So let's say there is increase in sales of ice cream is correlated to the number of fire incident, the fire breakout that has happened uh, in a year. So, considering the time of the year or a month, let's say in the month of May, my number of sales of ice cream has gone up, and also the fire incidents has also gone up. So logically, you can infer that there is no correlation between the two, and there shouldn't be. How can ice cream consumption could actually proportionate with a fire accident in a city? So there shouldn't be any correlation, but in this case, you are getting a correlation. The reason for this being May is a warmer month, and in the warmer month, you might expect to have more people consuming ice cream, and fire accidents are also quite high in a warmer month. So they directly are not correlated, but there is a third factor or a third variable which comes into picture: the temperature. So, whenever there is a correlation, just don't take it into your equation just because they have surprisingly high correlation number. Also take into consideration that there could be a third variable. There could be a possibility that a third variable is influencing these two. So that needs to be kept in mind. You should logically also think that whether considering only these two variables makes sense or not. Also, there is one more example, like if I have KFC and McDonald in the same building. So, for suppose if KFC is earning more, so both of them have the same kind of products to provide or same kind of beverages to provide to customer. But it is seen that when KFC sales is high, McDonald's goes down because when customers start going to one restaurant, they don't go to the other. So sales of other automatically goes down. Similarly, if McDonald's sales goes high, KFC is expected to have a decrease in the sales. So both are correlated. Both have a correlation, good correlation. But should I say that is there any number in between two, or is there any relation between that? It could be possible that if KFC was placed a kilometer apart, then their sales wouldn't have been impacted at all. So it is only because they are in the same building, they are influencing each other. But uh, otherwise, there shouldn't be any reason why their sales should be correlated. So I hope I'm making sense till here. So these things you need to understand that just having a high correlation number doesn't mean that there is a relation between the two. You need to be cautious to some extent and also understand that there could be a third reason for it as well. Okay. So, so some concept on linear regression. So this is a simple linear regression where I have only one independent variable and an independent and a dependent variable. So my independent variable is x, and this depends, and my y depends upon this equation. So this becomes my dependent. Always remember that my y depends upon the equation, so it will be dependent variable, and x is independent of anyone else. X is not dependent, so that way it becomes an independent variable. So previously when I started learning a simple regression, I used to get confused between uh, dependent variable and independent variable. Uh, but as you closely look at it and try to understand that how is the association is and how it has been framed, the entire equation, you can understand that y is dependent on others and x is independent. So this way you can remember. So this is a simple notation that I have. My b naught or b0 is my intercept, the value of intercept, and b1 is my slope. B1 also signifies that how much change in x will contribute to the change in y. So suppose if my value of slope is quite high, then small change in x will impact a larger change in y. So slope also makes a quite high impact, and when you're looking at the equation of linear regression, the coefficient b1 should also be taken into consideration because it makes a quite good impact. But suppose if it has a very uh, small value, and then I could say that there isn't any significant impact of x towards my dependent variable. So these things you need to understand. So while judging a linear regression model that you have created, few things that you need to consider. One is the value of your slope that you are getting. So this is one of the major key things that you need to understand. Uh, R square and other things comes later, and also the F statistics. F statistics mainly signify the impact the model is making, or is it at all significant? Is it worth taking that model ahead and working with it? So these are the things that comes into picture with F statistics. So we will slowly get into all of this, and we will understand that how to judge a significance level of a model. So regarding making a linear regression, and one more thing, as I said earlier, simple linear regression is only when I have one independent variable. When my independent variable becomes multiple, more than one, then it becomes a multiple linear regression. So here is the linear regression technique that, or the concept that we have. Our main purpose to find the value of beta, for example, this beta naught and beta 1, although intercept and the slope, to optimize this value, it comes from this equation. Suppose this is my actual and the predicted value. I have the actual and I have the predicted, and I am getting the sum of square errors. So my linear regression should be uh, composed or framed in such a way that the value of A or the value of error goes down. The sum of square errors is minimum, and this is how we tend to predict the value of beta and beta naught and beta 1. And the equation that is used to determine that is the cost function. As I remember, there is a j theta and there is an equation after which you put into that and you get the value of beta and beta naught and beta 1, which has the least sum of square, which leads to the least sum of square value or sum of square of errors value. So our main goal is to optimize this or to minimize this, and on the basis of the minimum value that we get, corresponding beta naught and beta 1 value is taken. So I hope it is self-explanatory and easy to understand. So this is standard error estimate. So so this comes into picture when I have a variable, and let's say let's suppose I'm working with a simple linear regression. So let me take that only example, and I have my actual and my predicted value. And because I have only one variable, so my degree of freedom will be n minus 1. N being my number of observations that I've considered, and it will be minus 2. In case if I had more than one, then it should be n minus k plus 1, my degree of freedom. So this value, my total sum of square errors divided by my degree of freedom, gives my standard error. So this is the rough estimate of my standard error. And as you see, it measures the reliability of estimating the equation that is developed. So mainly what happens is when I have a coefficient and when I have a sum of standard error, so after that my t value comes into picture, which helps me to understand that how significant impact it is making to the model. And from the t value I get the p value. Okay, so is someone
Thank
saying
you.
anything?
Yeah, yeah. So to disturb you, can you again define the number of freedom? Like, how does it define?
Okay, so degree of freedom is so here, as I've said, it is simple linear regression. I'm considering only one independent variable. In that case, my equation will be n minus 2. Okay, For suppose if I have more than one independent variable, I have somewhat like k variables, k independent variables. So my equation will be n minus bracket of k plus 1. So if I tell you, so in that case, my degree of freedom, that will be n minus, sorry, this will be equal to n minus k plus 1. That will be my degree of freedom in that case, when I have more than one. So automatically, if you put the value of k as 1, it will become 2, and it will be degree of freedom will be n minus 2. And residual. So there is a term that comes into picture in linear regression, that is residual and fitted. So residual is mainly the error values, or the difference between the actual and the predicted value. And fitted is my uh, the one which I have got through my fitted line, or the uh, or my predicted value that is good, that I'm getting is my fitted. So here comes into picture my sum of squares, and after sum of squares I have r square. So r square makes a significant impact in linear regression. How it does and how it is, we will see. So for suppose you have this line, mean value of your y response, and the sum of errors, or the total uh, sum of squares, will be the entire value, the actual value with its deviation from mean, and then sum of square will be actual value minus your predicted, the sum of all that values, and sum of residuals will be this, my predicted value to the mean value of y. Questions at so my equation somewhat looks like this. Like I said here, so this is my total sum of squares. So this is my total variance, or uh, my I, or the actual value, that is minus of my main value, and sum of squares. So total summation of this. So this is my SST, or total sum of squares. So that will be equal to my unexplained variance plus explained variance. And so this will be my fitted value, and this is my actual, and this is my main value, and this is my fitted value. So this is how, and it should be square here. I think it is missing. So this is the entire formula, that SST is equal to SSE plus SSR. So hope it makes sense. Okay. So uh, any question? Okay. So in while developing a model, I have certain parameters that I need to into consideration. My R square will always keep on increasing as I increase my number of variables. So more the number of variables, more the dependency of that model becomes on that variables, and better will be my R square. So for example, if I have some 6 variables and I include all of them, my R square will be somewhere around 100%. but that is not desired because I have fitted my model with all the variables. So what happens is my model becomes overfitted. So my model has all the information, but when it goes to out of bag samples, I'm not able to predict accordingly. So here is a mitigating factor, or a factor which has a better goodness of fit, or a better indicator whether I should be taking that variable or not. So here is my, okay, just a minute. Okay, okay. So just just a minute. Okay. So let me start again. Before getting into linear regression, there are some assumptions that you need to consider. Like first assumption is linearity. So my plot between my y variable and x variable should be a linear one. So you can see here this graph that I'm getting, or the scatter plot that I have plotted, is a polynomial type function that I'm getting, right? And you want to fit a linear line to a polynomial line. So it is expected that your model will provide a lot of error. So it is not worth taking it. Instead, what you can do is you can take copies of the same independent variable, make further more transformation of it. For example, like square root, or uh, square it, cube it. Then it will become a polynomial function. But here, fitting a polynomial line with a linear line would help. So that is why you need to consider that both of them should be linearly related. If not, make some transformation to your data, like make it a polynomial of some degree, make it a square root. So these are some of the transformation that you need to do. So first assumption is our linearity, and also when you go for an interview, you will ask with these questions that what are the assumption in linear regression. So people do linear regression, but they are not aware of all the assumptions that are there. So this is the first one, and this is quite important from interview perspective. Normality. So one thing is that residuals are actually your error values. So your error should have a normal distribution. So what it means is my error should not have any pattern. All my errors should be concentrated near zero. So it should be concentrated near zero, and as the value goes up or goes down, my uh, strength of the error should also go up or go down, or the magnitude that I'm getting should also. So it should resemble a linear, or I'd say a normal curve, normality of error, a normality of all the residuals. And also for your distribution of your y variable should be normal, corresponding to the x variable. Second is normality. Third is independence of assumption. So this is what happens is, let's say, so let me explain in this way. Uh, Here independence mean that, for example, I have a value, value at some t value. So my value of y at t equal to t, is somewhat dependent on my value of y at t minus 1. So you can see it is autocorrelated. The dependency of y is upon itself, on its previous value. So this should not be there. For a linear regression, that dependency of y variable upon itself shouldn't be there. Otherwise, it comes. This actually is taken care in time series. So when we will be covering time series, then I will show you that when graph or a equation or some my predictor variable is dependent on itself, then it becomes a case of time series, and then we follow some models like ARIMA or Hall-Winter, or I can say, so mainly it becomes a equation or a problem of autocorrelation function. So this shouldn't be there. Autocorrelation shouldn't be there between my uh, and dependent variable. Fourth is my homoscedasticity. Homoscedasticity means as my value increases, it should have the variance here should be same. So no, here if you check, what happens is as it is increasing, the cone or the funnel part is getting broader, or the variance part is getting broader. So this shouldn't happen. It should be like uniform variance should be there, something like this. So this is desired. So to check homoscedasticity, you can have a scatter plot, and you can check that how it has the variance is there. And also we have some plot later on uh, related to the model, using which you can check whether the my model is having the homoscedasticity or not. So these are the few assumptions. And also the final thing is multicollinearity. So multicollinearity is there shouldn't be dependency between the independent variable. For example, if my x1 and x2 both are dependent on each other, and I have put both of them in my linear regression formula, then it will tend to overfit my value of y. Instead, what I should do is the one which is making more significant impact, I should consider only that and remove the other. So in that way, what happens is my model becomes quite robust. It is quite flexible and easy to adapt to new values. Or when an out of back sample comes in, it is easy to, it is good to adapt to other values. So multicollinearity shouldn't be there, and best way to check is through VIF, variance inflation factor. So here is multicollinearity. So all this dependency shouldn't be there between independent variable. All should be independent of each other, and a model which has least number of independent variable should be chosen. With least number of variables, if you can explain all the variance, then that should be the best model to choose. And there is a concept of parsimony. Parsimony means you can say थोड़ा कंजूस रहना, and you should not allow all the variables to pass into my linear regression model. Only variables which makes most significant impact, which are worth considering, should only be taken. Otherwise, taking all the variables would actually inflate your R square value, and it will tend to overfit. So these were the some major assumptions for uh, linear regression. So let us take one example. Let us work on it and try to understand how it works. And also one thing that I have not mentioned here, that of all the methods to choose the perfect model, uh, R square is one, but it shouldn't be the final version or the final take. Apart from R square, you should consider root mean square error, means, and sum of square errors. These are the two major things that you should look at. Root mean square error should be the most prominent one to understand. So let me take here one example and let us try to understand. So just wait for 2 more minutes. So here I've taken a data set Toyota. So here I have price, age, that how many months it has been, and how many kilometers it has driven so far, what kind of engine it is, what kind of fuel type it is, horsepower, color, metallic color or not. So it is mainly a factor variable which shows that what kind of color it is, automatic gear or not, cc, number of doors and weight. So including all these things, we need to predict that what should be my price. So this is my I would say dependent variable, and all of these will be my independent variable. And let us need to understand that how it should work. So far what we have studied, we will try to implement and try to understand that how we can make a good analysis and how we can choose the best variable which will explain my price of the car. So let us proceed. So this is just a estimate or a rough view of how my variables are. So if someone is not speaking, please go on mute. I don't know from where I'm getting this background noise, but if you are not speaking, please go on mute. Anubhav, Saket, yeah, Saket. Thanks. So this is my data set. Let us check the summary and let us try to understand what is there. So price, my minimum price is this 4,315 and it varies till 32,500. Age is between 1 to 80. Kilometer, minimum kilometer is 1, so it is a brand new car seems like, and maximum is 4 lakh, so sorry, 2 lakh 43,000. Fuel type is mainly 3. Here I have CNG, diesel or petrol. Horsepower again, weight, doors and so on. So automatic, it should be my factor variable, it shouldn't be like a numeric one. Same with metallic color, I need to change this. I'll take care of it also. And if you see the variance of my price, so this is how it has been distributed. So it is a kind of right skewed, the tail is towards the right side. If I make it a better plot, so this is how it looks like. So now what I need to do is I need to create a dummy variable. So what happened is here my fuel type is either of the three. Either is it is diesel, petrol or CNG. So but for linear regression, this factor variable won't work. I need to change it to my numeric variable. For that, what I will do is there is a rule of thumb that you always need to understand. If you have n factor variable, then create n minus 1 dummy variables. So this is the rule of thumb you always need to remember. Here I have three factor variables of fuel type. So what I need to do, I need to create two dummy variables because the third one will be mirror image of the first two. For example, if first two are already 0, then it is quite obvious that my third one will be 1. So it becomes a mirror image. Like for example, if I have a factor variable which says about gender, it is male or female. So in case if my gender is male, I am putting up 1. So already in the case of 0, it will be female. So it becomes a mirror image. I don't need to create two separate variables for that to flag male or female. So hope this makes sense.
Ankit, just one question.
Mhm.
Like rather than creating n minus one dummy variables, like
Mhm.
suppose if you want to create a numeric,
Mhm.
so if we can assign like diesel as one, petrol as two, and CNG as three.
No. That will have a different meaning. Uh, what you said, I understood, but that will have a different meaning. So let me tell you, if you're saying that diesel should be one, petrol should be two, or CNG should be three, then why not diesel should be half, petrol should be one, and CNG should be 1.5. I can change the scale as well, right? So why not that? So uh, rather than, or let me say, diesel can be one, petrol can be three, or and CNG could be four. So if I'm making a scale like this, or they are equally separated at a equal interval, then it could be possible that I'm not getting a, I'm not impacting the correct thing, or the scale might be different when I put it into a linear regression model. It could be possible. For that reason, let's not make a equally separated variable, and what else we can do is make a dummy variable and it will take care of it. So what I
Okay.
said, you got it, na?
Yeah, yeah, yeah.
So that is the reason we cannot take that. Even for the first time when I did a linear regression, I thought the same. Why not do that? So now after that, when I did many more case studies on linear regression, I realized that uh, method is not applicable at all for obvious reasons. So here, let me create this dummy variable. So here I flagged that on basis of my fuel type, this will be so and so. So fuel type 2, it is diesel, correct? So now I don't require my fourth variable. That is this. I've already flagged them. So I'm removing the fourth one. And let's see what is there in the auto. So I've removed my fourth one. Now let us check what would be the plot of price and age. So you see there is a downward or a negative relation between them. It is moving down. Similarly, if I make a correlation between the two and try to understand, and then auto price with auto age. So correlation is quite high. It is negative of 0.87, which is a good number. So it is a good determining factor that it is making an impact. So age is my determining factor for the price. Let me take kilometers as well. Now it is also obvious that if the age of a car is quite high, then kilometers also will be high. Now here I make a correlation between the two and try to understand. So though a bit less, but still a moderate significance. with horsepower. So horsepower here is a issue. I have only some factors of number. That is why I'm getting it like this. So what it means is, so here I have only few levels of, so it starts with 69 then 71. So it starts with somewhere here, then 71, 72. So you see, it's not a kind of continuous variable. It is a kind of factor, but still, the more, I'd say, a better method to look at it would be a smooth scatter plot. Smooth scatter plot. So it will show me the density, where it is more placed and where it is less. Okay. Mm. So it has been done like this. I've changed the axis somehow. Let me switch it back to that. So yeah. So again, even if I look at it, whether here what I've done is I've made the density of it. So where it is more closely populated or population is quite high, it becomes darker, and the faint one, the population is lower. There is a slight increase, no, then goes down. Then towards the end, it is quite high, but still I don't get a significant impact or a significant trend here. So may not consider this. Let me plot with this here also, because it is either 0 or 1. So no such significant variance that I can see. Now let us check with automatic or not. Again 0 and 1. So nothing significant that can be seen. Though for automatic, it has only lesser range. For not, it is higher. It has a higher range of price. Price with CC. CC is also, as you can see, is a discrete one. Some values are there only. Doors, I'm also expected to have the same thing there. And weight. So with weight, so a simple understanding here would be that with my weight, uh, my size of the car will be quite high, and when the car is quite spacious, the price is expected to go high as well. So here it could be possible that I could see some trend. So let me try to do it a correlation between the two and try to understand the how well it is correlated. It is wait. So again, not a quite a moderately correlated one. So now let us do one thing. Let us take all the variables that we have created so far and try to understand that how my model would look like. So it was a small data set, so that's why it has taken all of, quite easily. So here you see my multiple r square and adjusted r square are quite. So first of all, let me start from here. That as I said, this is the beta value or the coefficient of this variable. So all of them you can see are to the power of exponential to the power. So 10 to the power 3, 3. So quite a high number. So in a way, they are impacting quite high comparatively, except for this one, which it has only a 10 to the power minus 2. So, Govardhan, it is on the basis of correlation value that I have just created so far. So, I have just executed this correlation, and on the basis of it, I am getting this correlation number here. So, this basis I am saying that it is highly correlated or not.
Yankis, Ankit, I think this last for 2 minutes your voice was breaking. So can you just explain that intercept concept and all?
Okay, okay, fine. So, is it fine now?
Yeah, it's fine now.
Okay. So you remember that I said that to determine that which variable is making more impact, first we should look at this on the estimate one, or how much impact it is creating. So first of all, these are my slope. For age, it has a slope of something and 10 to the power of 2 kilometers like this. So these are the slope, and how much change of age will impact my uh, change in price. So that is why you should look at the estimate, and also the value. The value here, negative or positive, signifies that whether it is a positive relation or a negative relation. Whether varying this will positively impact my price or negatively impact my price. So here you can see, as my age increases, my price is expected to go down. So that is why it is negative. For my kilometers as well, if my kilometer goes high, then my price is expected to go down. So mainly it is related to aging, and also as kilometer is high, then car has been used a lot. CC CC is very less, I would say, to not a quite high impactful one. And doors also less. And here I have weight and fuel type. So negative means uh, is it making a positive? Is how the sign means mainly how much impact is making in which direction. So this is mainly about estimate. This is the standard error which I showed you the uh, equation just before. And when you divide this, you will get the t value, and corresponding t value will have a p value. And on basis of this, you can understand that how much significant that variable is. And coming to F statistics. So here I have 10 variables, and total degree of freedom is this. So it is my total number of observation that I have, and degree of freedom plus 1. So number of variable is 10 plus 1, 11. That is uh, 1436 minus 11 would be 1425. So this is my degree of freedom here. And on basis of this, I'm checking that my p value is less. So this model is making a significant contribution. And also my R square and adjusted R square are quite closer to each other. So let us look at some of the other transformation, and let's see what else we can do with the data set. So here I am splitting my data into a train and test, and trying to predict with using all the variables that how good it will do. So in train, I have made a sample of for all the I would say variables, or all the number of observation. Among that, only n1 I have chosen. So among 1436 I am choosing only 1000, and that is randomly placed. So let us understand what is there. So I've just picked all of them, and now I'm trying to predict that on using the same model on another dataset. So the one excluding the train, let me try to predict and understand that what it has done or what it has provided. So this is my main error. So a good model with a definition, or a likely a good model would be where I can minimize my root mean square error, mean error, and mean absolute percentage error. If these parameters are reduced, that will be my better model. R square is also a good measure of significance, that how much variance I can explain. But main purpose would be how much I can explain, how much I can reduce my error. So currently I've used all the variables here in this. And now let me work only with age, because even age was able to explain most of my variance. Even with age I was getting a good correlation. So let me try only with age and try to understand how much of error I am getting. Mean error has reduced, root mean square error is less. So when I'm taking less variables, see these are reduced. So always my motive would be to take minimum number of variables, and using which I can explain the maximum variance. So here what I'm doing is, it could be possible that the variation is not a linear one. It could be a non-linear one. As you can see earlier, see here the variance, it could be possible that it is a non-linear one. So using this, so it is not a linear one. It might be varying somewhere like this. Could be highly possible. So let me do one thing. Let me take the square of the age, and with that let me try to predict that how much variance I'm able to explain. And now if you look at the kilometers, also the same trend, something like this. A square variance is quite likely here. So let me take square of it and let me try to predict on basis of it that how good my model is. So first I'm making only on the basis of age and kilometer. what summary I'm getting. So my R square and adjusted, so somewhere around 79%, which is okay. I'm able to explain most of the things. And also because kilometer itself is a quite high range, starting from very less value to around 2 lakhs. So uh, having a coefficient of 10 to the power minus 2 is explanatory, quite explanatory itself. So let me do one thing here. Take square of age and square of kilometer, and let's now try to check that how much variance I'm able to explain here. Now here, as you can see, now kilometer doesn't make much of an impact when I'm considering square of kilometer. The significance level of kilometer has gone down. As you can see, the p-value is quite high, around 50%. So it is good to drop it. I can afford to drop this because it is not making any impact. So here, as I said, square of kilometer is only making a good impact, and kilometer is not making an impact here. So it is good to remove that. And after removing that, let us see how much impact it makes on my model. Okay. So here, see the R square hasn't changed much. Here I was getting 8.3 and almost the same R square, 8.3. So removing kilometer was a better option because uh, it was not contributing at all. And as I said, with least number of variables, if you can explain the maximum variance, then that should be chosen. The more lighter your uh, model is, the better and the more robust it is. And as you can see, all of them are making a quite a good contribution. So this is residual versus fitted, and as I said, there should not be any, I would say, uh, a relation, or I would say any pattern that should be there. So here, even you can see there is no pattern at all. That pattern is missing, and that is what is desired. If there is a pattern like linear or somewhere like downwards, then I would say that my model is a bit biased. But here, no pattern, so good to go. And my residual is also a kind of normal. So this is my distribution of residuals. So let me explain it in density. So you can see this is normal and most of are concentrated near to zero. So this is what is desired. That normality of error. The error doesn't have a pattern, which is good. We have also achieved that. So there is no bias in the model. Here also the same thing. So here I was working with 1 1. So the previous one that I've taken. So that was quite unbiased. But even here as well, I don't see much of a pattern here. And here also, if I plot density of M12 dollar, so again, even a better graph. So you see, it is even a better one than compared to the previous one which I got. Finally, if I look at the third model where I've considered only kilometer square, not kilometer, and if I try to judge it, that how good it is. So more or less the same thing. Could be a slight difference, but yeah. With less number of variables and only precise one, I'm getting even better. Though not quite very significant, but yeah, even a better resemblance of a normal distribution. So a rule of thumb here would be keep minimum number of variables that you have and only choose the best that you can provide. And also if I look at this for my third model, it's the best one that I've chosen so far using. Also the pattern is, so pattern here is more random compared to other. Here it's all congested and here it is all spread out. So no significant pattern at all. Even better than previous distribution that we have seen. So here it was more congested and in the previous one even more of congestion. A good residual versus fitted plot would be that all the points are spread out evenly throughout, or randomly, I should say, not evenly, it should be spread randomly. So that is the best graph that you will get for a residual versus fitted. And that actually explains that there is no bias in the model. So this was one of the case study. Let us go back to the theory and understand few more things that we have missed out. So there you remember that there was a p-value related to each and every variable that we had. So each variable is making a significant contribution or not, we are coming to know through the p-value of it. And how that p-value is obtained, this is through this hypothesis testing. So here my hypothesis or the null hypothesis is that the slope of that variable is 0, or that variable is not making any contribution. My alternate hypothesis is that it is making a contribution, and for that I need to know that how much it is, or should I exclude or include that variable or not. So this is my hypothesis that I've stated. And here what happens is, in the example, so let me go back to that. So here I have estimated the coefficient. So this is my value of beta, and here is my standard error. So what happens is when I divide this estimate with my standard error, I get the t value just by basic division. And on basis of this t value, I have a corresponding p value. So in last class, if you remember, for the t table that we had, for every particular value, we had a particular p values. And on basis of that, we get the significance probability value, and hence we can understand whether this variable is at all making any contribution or not. So let's go back and theoretically let us understand that what is there. So here it is the sum of square. Sorry, the standard error that we have, and here it is the degree of freedom for only one uh, or a simple regression. The case that I've taken here, this is a simple linear regression. This will be n minus 2. For a multiple linear regression, it will be n minus k minus 1. Here you can see degree of freedom is n minus k plus 1, where n is the number of observation and k is the number of variables, the independent variable that I am taking. So this will change accordingly. And using this, I get my standard error. And in the t statistics that, or the t score or the t value that I've got, I just divide by coefficient with the standard error. So all of you must have done some linear regression yourself also. So just try to, so let me do this and try to see what I'm getting. So see, I'm getting minus 33.4. So what is the value that I was getting here? Yeah, more or less same. It could be because there are even more further terms after the decimal points, which I have ignored here, and they have rounded it off. So that could be the reason. But otherwise, yeah, this is how it is calculated. So for 8 square, let me see and show you. 18.99, and what I was getting there, it was 18.99. So this is how this t-value is calculated, and after that the corresponding p-value has a p-value. So this is how this t statistics or t-score is calculated, and after that I have a corresponding p-value using which I can check whether it has a significance at all or not. And this is my f statistics, which comes later in the linear regression, that it checks whether the overall model, how good it is and is it useful or not. In this case, if I am getting a pay value lesser or more than 5%, then I can reject my model and say that that model is of no use and I should try with something else which makes a better impact. So few things about overfitting and underfitting. I've already said that underfit is when there are few more variables required, but you have used only, for example, yeah,
I have one doubt.
yeah, tell me.
So, yeah, where you have mentioned that about the null hypothesis.
Mm-hmm.
So you told me that a null hypothesis for the always slope is zero. The slope is zero. It means there is no dependent with the independent variable or the independent variable.
Correct, correct.
This is the standard. This is the standard rule. Yeah, maybe according to the requirement, a statistic will be defined.
Yeah, it is true. So, see, my null hypothesis can vary according to the different situation. In this case, for the beta test, the significance of the variable, the null hypothesis is stated in that way that it doesn't make any impact. Further, one day I was reading that how the null hypothesis is said to be. So, in that, what happens is the null hypothesis is something that we always tend to reject. Uh, or most of the null hypotheses are formulated in a way that it should be rejected, and a p-value that should we should get that should mm, I would say uh, uh, contradicts the null hypothesis, and we get the conclusion as alternate hypothesis. So in most of the cases, it has been formulated like that, but that is not a, I would say, a standard one. But in most of the cases, yeah, I have seen that. And also here, if you see that my null hypothesis is accepted when my p-value is more than 5%, or I would say it is not making a significant contribution, and I don't have any such evidence to reject my null hypothesis, and I am accepting that it is not making any contribution. So here my p-values are quite less, so I have to reject the null hypothesis that it is not making any contribution. Instead, it is making a contribution, and my null hypothesis is rejected. So it's okay. Should I proceed or
Yeah, it's fine.
okay, okay, okay. So here is an example of overfit and underfit model. So here you can say it is a polynomial mm, distribution, and I am fitting it with a linear model. So as expected, it will be going to an underfit model. And now, if you see, here I am having a polynomial model and I am fitting it with the polynomial model itself. So it is just the right thing that I need to have. But now what happens is if I overload it with too many variables, here, if I overload it with too many variables, the dependency of that model becomes quite, rigid. It is dependent on too many variables and it won't be that adapting to the new situation or the new values that I will be throwing at it. So it becomes quite overfit and basically the bias is quite high. So in this case, we have to over or anything which underfit should be rejected and overfit should also be with minimum number of variables and how much I can explain. That is the main funda here to choose the number of variables with minimum variable maximum variance. And if I see that there is no much contribution towards late I would say variables, then in that case those should be rejected. So let us now move to one more data set and try to understand. So this is on empty cars. So empty cars, most of you must have heard about this data set. So here in empty cars, if I view this, here I have a car and in this car I have a few of the features. So these are basically my row names and with this I have miles per gallon, number of cylinders that I have. Then this is also one of the features like displacement, horsepower, draft, weight. I'm not sure what it means. And this should be a factor variable which is either 0 or 1. Again same thing 0 or 1 whether this feature is present or not. And gears also it should be a factor because gear is minimum 3 and maximum 5, not a continuous. And carb is also looks like a factor 1. So let us see and let us try to understand that how well we can explain the variance here and how well our model will go. So here if you see the miles per gallon, the mileage that I have. So for third number gear it is at this point. For fourth number it goes high and then fifth number it is a bit low compared to my fourth one. So not a significant relation that I can say, but for fourth it is obvious that it would be more miles per gallon. So here I make some changes in the model that I'm using. I have made my cylinders into a factor. AM as a factor, as I said, it is either 0 or 1. Gear also factor, so it is only 3, 4 or 5. VS is also same factor because I have only 0 or 1. Same thing with carb. And let us now look at the structure of the empty cars. So here I have made most of them as factors. So it has been transformed accordingly. So here if we see again a kind of a slope or a relation between the two, but again it's not a quite a linear one. I would say a polynomial kind of or a square would explain it a bit in a much better way. But though there is a variation, but not a linear one. So I think I need to transform my variable and then need to test on it that how good it will go. So correlation is also quite good. So let us create a model only using weight. So I'm explaining my mileage using the weight of the car, and it is quite significant because, as you see, uh, even in the case of a motorbike, if my bike is less weighted, the mileage is expected to be high because that chemical energy is converted into a kinetic energy, and less the weight, so less kinetic energy will be provided. So m, or the mass of the car, becomes a factor here. So that is why it is expected that weight will be proportionate to my mileage. So yeah, as it was expected. So quite a good variation can be, or quite a good number of variants can be explained only using my weight. So only I have used one variable, and it explains around 75% of the variance. So it's quite good. So let us plot that and explain. And also, if you see, you're getting a kind of linear type. An AB line will also show you that this is quite a good, not quite linear, but yeah, mostly. And also one good thing, if I tell you here, uh, so correlation value is this 86 point. Now what I do is, if I make the square of this, I am getting this 75, and this, if you remember, this was my r square. So r square is mainly if there is a correlation between my uh, uh, I would say my predicted and exact value, predicted and my actual value. So that correlation between the two is my r square mainly. So in layman terms, if I remove all the formulas, then this will be my r square, my correlation between actual and predicted. So these are mainly coefficient that I have. So coefficient is only this. So here, as you can see, it is already mentioned there. Coefficient, residual, and fitted value. So let me take one more model here, try to understand that how it is behaving. Here I have weight and this displacement uh, variable. So contribution is not quite high, and if you see there, my r square was around 75%, and I am not getting a significant impact here. It shows that it is more than 5%, bit more than 5%, but yeah, it is not worth considering. Also, my adjusted r square is not significantly impacted. For 75, from 75 it has went to 76 only. So I don't think this variable is worth considering when I'm already taken weight. But somehow let us load it with some more variables and try to understand that how it behaves now. So now see, this variable has almost disappeared. So the reason being that the impact that was there due to this variable, this what is now shared by weight and HP, horsepower. So these are able to make all the impact that was previously done by this. So, and that is the reason it has become quite insignificant. So now let us remove that and now try to understand that how my model is. So you see, r square hasn't changed a much, and also r square and adjusted r square are in close proximity. So it is good to remove that variable, and that was of no use. Now let us check a correlation between all of them and try to understand. So this is also having similar correlation, same. So here what happens is a similar kind of correlation, uh, same variance is explained by weight and same by this. So you can exclude one of them. And if I check with the weight and disp also, the correlation value is quite high in between them. Weight with disp is quite high. So it is good to ignore one of them. And in case if I consider only with horsepower and weight, the correlation is quite less, or you can say a bit moderate, not high. But considering with horsepower and my mileage, miles per gallon, it is more. So seems like horsepower is worth considering rather than this. So this is also one fine plot. So with all the variables, I've seen that how it varies. So here even you can see it's per gallon with weight, good variation. And also display, if you can see this is a square kind of variation, not a linear one. A square would suit here more than other. Here it is a bit linear type only. So what we can do is we can try a square transformation on this and then try to understand that how the variance is. So let us do that and try to see what is the summary of it. So now see, it becomes more impactful.
Yeah, yeah, Ankit.
Yeah.
Yeah, I just have one doubt.
Mm-hmm.
So suppose that in the model,
Mm-hmm.
when I saw that MPG is the dependent variable and another three is the independent variable.
Mm-hmm.
So all MPG with the all remaining variable,
Mm-hmm.
all are the high correlation with the MPG.
Mm-hmm.
So how they at the time of the correlation,
Mm-hmm.
when we always plot the sum of the table of the correlation table we plotted,
Mm-hmm.
then how to check the this variable will take, yeah, which variable will not take. So we
Okay.
know that if correlation is high, then we have to discard the particular variable.
Mm-hmm.
So that time we have the some of the weight with the DSP. This
Mm-hmm.
is the high correlation.
Mm-hmm.
So how that in between the correlation of the independent variable is low required for according to model.
Mm-hmm.
But how to this particular variable
Okay.
for at a final model?
Okay. So yeah, so this is a good point, that because just looking at the number, for example, so even I was going through many articles on this, many book or so there what it was written is that correlation value between the variables, for example, weight and horsepower, if they have a correlation of around 90, then one of them should be omitted out. So in this way, you can see. Another is variance inflation factor. Like I said, to remove multicollinearity, variance inflation factor or VIF is used. So using that, if a VIF value is more than, let's say, 3, in some books it is written 3, some books it is written 5 or 6, some books it is written 10. So using that as a threshold, you can understand that which variable you should keep or which variable you should omit out. So this is also, and last is my Akaike information criterion, AIC. AIC, what it does, all the noise or the information loss it takes care of. So if for example there is variable which is not useful, it's redundant, and I need to remove that, so AIC or a Kaika information criterion would be a good method to remove that. So I will come to that AIC, step AIC, how it is done. So this is part of this case study as well. So just to do that as well.
Yes.
So here, this I'm getting a residual one. So a residual, as I said earlier, there shouldn't be any pattern between residual and the variable. And even if you see here, residual with other variables, they are pattern free, more or less pattern free. Now, ANOVA is a good technique to compare two models. So if I have stored my linear regression in two of the variables, then ANOVA can be used to see which one is more significant and which one is not. So here what happens is statistics is a very good comparison between the two models and tell us the significance of the difference. The one with the lower this sum of square is better one, and if suppose there is not much difference in between two, then choose the one with uh, fewer number of parameters. So this is called parsimony principle. Parsimony means being a miser, or in Hindi it is said kanjus. So when you don't spend much, then you are said to be a parsimonious. Same similar concept here as well. So when you don't let all the variables get into use, the principle become parsimony, where you spend less on the variable, and this is quite spend less on the model, and this is to a bit extent required, because if I can explain with less number of variable, I should use that. More number of variables unnecessarily, then it will hamper my model. So let me do an ANOVA here as well. So one with the lesser one. So only problem here is this ANOVA won't work for two models with same degree of freedom. So here what I'm considering two variables here. So here there won't be any significant impact. Only good thing is that when I have a dissimilar number of degree of freedom, then it becomes quite handy. AIC is information loss, or the AIC value that I get for each model. The one with the minimum AIC is a good estimate. So mainly when I do a step AIC, it reduces that information loss. And let me do with one more model as well. So let us try to understand that all the graphs that are there associated with a linear regression plot or model. So this is mainly residual versus fitted, and as I said earlier, the pattern should be scattered all over. The point should be random in nature. There shouldn't be any pattern. QQ plot and this one, this standard residual. So this is mainly after standardizing the residual part, that is making it on the scale of 0 mean and 1 standard deviation. If I do that, then this is mainly my standard residual versus fitted value. Both resembles the same thing, but in a different representation. And here also I should have all of them randomly placed. QQ plot is mainly my normality of error. So whether I'm getting a normal pattern or not. So this is my standard residuals, standard errors, and with a standard normal curve, if it is following that pattern or not. So along the line, my plot should be this along the line. If it varies away, then I can conclude that it is not normally placed, or my residuals are not normal, or it is having some pattern. So ideally, it should be along the line. Residual versus leverage is actually for a far point, or you can say, uh, I would say, to see is there any extremities in the model or not? Is there any extreme values or not? For example, if I have a log function, so first of all my value is less, then it becomes high, high, and higher. So is that kind of any extremities are there or not? If it is there, then I can make certain transformation in my model and display accordingly. So square or log transformation are a good way to say that. So I've mentioned all these things in the R script here as well. You can go through that and try to understand. So coming to the part that Sashi said regarding choosing the number of variables which are optimum and which to omit. So let us do that and try to understand. So in the model number 6, I have taken weight as cylinders multiplied by AM. And let us see if there is any uh, multicollinearity here as well or not. So cutoff mainly it varies from a certain limit. So at some stages it is considered that anything below 6 is preferred. Anything more than that shouldn't be considered at all. So here what happens is I've taken a product of both of them. So that is why it is getting like this. But if I consider that my VIF to be less than 10 or threshold to be 10, then most of them seems okay. So this is one method to look at the multicollinearity. One. Another could be this Ekaika information criterion to remove the unwanted variables.
Ankit, just one thing. So wherever we have VIF
Mhm.
greater than 6, those have a high multicollinearity.
Uh, Regarding the threshold of VIF, there is no common consensus about among the authors. So what happens is some authors consider 3 as to be the optimum level. Anything more than 3 or any variable having a VIF more than 3 should be omitted out. Some authors say that 6 is the correct value, and some say that 10. So it depends from author to author, and even for some cases and some websites I've seen that there is a variation. Some consider 6, some consider 10. So I would say there is no common consensus. If if you find that considering 6 is too high, then you can go with anything less than 5, or even you can consider 3 as well. So it is up to the person who is creating the model what he thinks about and what decision he takes.
Okay.
Okay. So let me use all the variables and let me do a KIK on each of them and then understand that how it is removed. So here I've taken all the variables, and if you see, not all the variables are a good estimate of my model. So here you see, when I've considered all the variables, sorry, my R square has gone up to around 90%, but here my adjusted R square has fallen down. So previously in the class, I already said that it is possible that adding more number of variables, your R square quite might go down, and your R square might go up, and your adjusted R square might go down. So it would happen like that. And this is a perfect example of my R square getting inflated, but my adjusted R square going down. So this is my step AIC. So what it does is, AIC is mainly a calculation of information loss. So here I have all the variables, and it has removed some of the variables then. And with each removal of variable, my AIC value is getting lower and lower. So all the variables which are not into consideration or not making a good impact are getting removed. So every time it is getting lower, and lastly I am left with only these 4 variables. So these are making the maximum impact, and that is why we have considered only them. So now let us check summary of the final model that I have got. So even here also, uh, cylinder 6 is making a good contribution because I've converted them into a factor. So if my cylinder is 6, it is making a good contribution, but cylinder 8 is not. And AM is already 0 and 1, so no need for that. So it is already converted into a factor. But anyway, here it shows. So just see from where we started previously in the model, where I've considered all the variables, my R square was 89% around. Adjusted R square was 77, and but now I'm left with only 4 variables. Yeah, only 4. These 2 are mainly repetition of of the same thing because it is a factor. So it has come down to 86%, and my adjusted R square has gone up. So this is a good way to, you know, optimize your model. So AIC is one of the good practice that you can do when you have a lot of number of variables, let's say around some 15, 16, and you don't need to scrutinize each of the variable separately. What you can do is apply AIC, and at the end, just look at which are the variables which are making a good impact, and should that be considered or not. And now if I plot them, see. Here, so these are the 2 extreme points where I'm getting a bit variation, but apart from that, it is following a good normal curve. Distribution here is also random. It is randomly distributed. It has also flattened up, so good. Here also same thing. Only thing is that, see, these are the car which have certain extreme values like Toyota, Fiat, Imperial. So these are few of the cars which are only quite showing a bit of abnormal trend. Apart from that, everything looks good. So this is all for today, and I've included one more example. You can go through this of your own. So this is about fuel efficiency. A similar example. So I've taken here first example and third example. Second one I'm not taking. You can try it of your own. And our scripts are already uploaded. You can go through them, and this one, it will be good if you practice that. So any questions?
And also have one doubt.
Mm-hmm.
So when there is also have a one error,
Mm-hmm.
residual assembler error. So I consider as a residual assembler error, or a root mean square error. So for a best model choosing. So which factor will choose? Residual error, yeah, root mean error.
Uh, See, this residual standard. So this is mainly for graphical purpose, mainly to. So main purpose our would be to minimize root mean square error. As I said earlier, minimizing that is the best way to get to the uh, you know the good values, or to minimizing all the errors that can be produced. These parts only look at whether it is following a normal pattern or not, whether my model is biased or not. So, like I said, in all the five assumptions of linear regression, so these comes into picture. Whether the variables that I've considered are good enough, or whether it is good to continue with those. So mainly these things are counted with these graphs. If you are considering RMSA, RMSA is one thing that we need to minimize always, or always purpose, or always intention in any model that we are working with to minimize that RMSA. Root mean square error should always be minimized.
Okay. Okay, thanks, Ankit.
Okay. So regarding all the notes regarding linear regression, I have already uploaded that in the uh, classroom group, so you can find that. Tomorrow I will be continuing with linear regression, logistic regression. So even I expect to upload all the documents by tonight only. In case if it is there in any delay, I will do it tomorrow morning. So for tomorrow also we have the same plan. Could be possible that I will be taking tomorrow's session a bit early. So that might be the only change, but apart from that, everything remains the same.